Doing a bunch of stuff. All right, today we're going to practice a bunch of log and exponent properties. And here is the huge idea that you need. These statements are 100% equivalent. That is the whole idea of a log. A log is the inverse of an exponential function. So, if we have a to the b equals c, we can rewrite that as log base a of c equals b. And here's why. Alright, so here's the idea. If we have some exponential function, y equals a to the x, and we want to take the inverse of that function, well, remember what you do with an inverse. You switch places of x and y. So we would rewrite this as x equals a to the power of y. Notice we switched the location of y and x. That's what you do to write an inverse function. But then typically speaking, you want to solve for y, because we like to have our equations in terms of y, not x. And so the question then is, how do you get that y out of the exponent? How do we rewrite this as y equals something? And the answer to that question is, well, you use logs. That's what they do. We would rewrite this as y equals log base a of x. That's where the idea of that if and only if statement comes from. We want to rewrite x equals a to the y as y equals, and that's what a log does. Important things to notice. Notice that the base of the exponent, a, is the same as the base of the log right there. So for me personally, when I think about logs, I think about them in terms of exponents. So when I see this y equals log base a of x, I think to myself, I know that the base, a, to the power of whatever this is equal to, y, has to then equal x. I think about it in this order right there. And that's the big idea of logs. That's what you need to know. And now we're going to run through a bunch of properties about logs. So let's look at these four problems here and see how we can rewrite them using some of our rules that we've been talking about. So first one, 3 to the power of x equals 5. Let's rewrite that as a log. So remember that the log is going to have the same base as the exponent. The base of the exponent is 3. So we're going to have a log base 3 of 5 equals x, because remember how a log works. A log says take the base 3, raise it to the power of what's on the other side of the equal sign, x, and set that equal to the argument, 5. So we get 3 to the x equals 5 when we write this as log base 3 of 5 equals x. These two statements mean absolutely the same thing. And we can get a value for this by using our calculator. You might need to use the change of base formula, in which case you could say the natural log of 5 divided by the natural log of 3, because when you use change of base formula, you can use any base you would like, but on a calculator, ln is fine, or just hit the log button, base 10, that is fine as well. Or you could graph the function 3 to the x and graph the line y equals 5 and set them equal to each other and find their intersection point. And these look like a pair of glasses. And that's a nose, and that is nose hair, and that's a mustache, and then there's a little grin underneath. So it looks like it could be someone's grandfather, perhaps. I'm not really sure, and I'm not sure why I'm still drawing it, because we still have problems to do. So let's look at this next one. Let's rewrite this as an exponential problem. Well, we're going to say 2 to the power of 4 equals x. And so what is 2 to the 4th? Well, 2 to the 4th is 16. So this one we can actually evaluate here. And now let's do the next one, which says if you have two logs of the same base being added together, you can rewrite them as one log with that same base and multiply the two arguments together. And that is the log multiple rule right there. And now let's rewrite this as an exponential problem. Let's say 3 to the power of 3, so 3 cubed equals 9x. And we can solve this. We got 27 equals 9x, so let's divide by 9 on both sides to get x equals 3. And let's think about how we could have solved that another way. Think about this bit right here, log base 3 of 9. And that's basically saying 3 to what, let's not use x, let's call it y. 3 to what power gives you 9? Well, 3 squared equals 9. So 2 would be what log base 3 of 9 is. So this is really log base 3 of x plus 2 equals 3, or log base 3 of x equals 1 by going ahead and subtracting 2 from both sides. And then look at what we have. We have 3 to the first equals x. So again, 3 equals x. And we're going to get a little clever on this last one. 2 to the power of 2x minus 2 equals 8. We are going to rewrite this as 2 to the power of 2x minus 2 equals 2 to the power of 3, because 2 cubed is 8. And now we can see that 2x minus 2 has to equal 3. But why is that? Well, imagine if you took the log base 2 of each side, and I'm doing that so slowly. Boom. Well, then we could use our plog rule to say 2x minus 2 times a log base 2 of 2 equals 3 times a log base 2 of 2. And notice we could then say, hey, boom, boom, those are gone. 2x minus 2 equals 3. And also I recognize log base 2 of 2 is 1, so them being there doesn't make a difference. But this would work with a log of any base, actually, so that's kind of cool. But we get 2x minus 2 equals 3, and so 2x then must equal 5, and so x has to equal 5 halves, and I like this green. So we will hit all the special properties as we go through a bunch of problems right now. So let's see what we can do. And I'm only going to do them probably in one way, but there are often different ways you can simplify them. So just because you do it in a different way than me, doesn't mean that it's wrong. It could be a brilliant way to do it. So see what you can come up with. But I'm going to do all these however it makes sense to me at the time I'm doing them. So let's look at this. 4 log base 4 of 2. I'm going to simplify this by saying, what is log base 4 of 2? Well, that's like saying 4 to what power equals 2? Well, 2 is the square root of 4, so 4 to the 1/2 equals 2. So I know that log base 4 of 2 is the same as 1/2. So that term is going to become 4 over 2, which is going to become 2, plus log base 7 of 1. Well, that's like saying 7 to what power is 1? Well, 7 to the 0 is 1, and so I get plus 0 there, and then I have plus a minus, so I wrote that kind of awkwardly, but minus log base 4 of 16, which is saying 4 to what power is 16? Well, 4 squared is 16, so down here I am going to get minus 2. So I get 2 minus 2, which is 0. So this all just goes to nothing. Same idea, going to use some rules here to simplify things. So first log is saying 3 to what power gives you 81. Well, I usually just count out multiples of 3 on my finger. So I get 3 times 3 is 9, times 3 is 27, times 3 is 81. So this will simplify as 4 minus, well, notice here I have log base 14 of 14 to the 10. So I could plug it and pull that 10 out front. And then I have log base 14 of 14, which is just 1. So that's going to simplify to 10 because 14 to the 1 is 14. And then I have 8 times log of a big number, which is 100,000. And notice that there's no base written here. So when there is not a base written, it is implied that it is base 10. And so let's think about what this is saying. This is saying 10 to what power is 100,000? We'll think about it this way. I would have 10 to the first, 10 to the second, 10 to the third, 10 to the fourth, 10 to the fifth, and so 10 to the power of, I'm not meaning to write that. And so if 10 to the power of x equals 100,000, then that power needs to be 5 to get those 5 zeros there. And so that then becomes 8 times 5 because of that 8 in front, which is 40. And so I get 10 plus 40 is 50. That's not how math works. I get 4 minus 10 is negative 6, plus 40 is 36. Sorry that I can't do basic math. Sorry still that I can't do basic math, because that's totally not even how math works. 34. That was pathetic. Don't let anyone watch this video. Alright, same idea here, getting a little fancier though. Let's simplify this jazz. Notice that I have in the exponent here 4 times the natural log of x. Well, I'm going to rewrite that as the natural log of x to the 4th, because then notice I have e to the ln, which are inverses of each other, so this will simplify as simply 2 times x to the 4th, because e and ln are inverses, so they undo each other, so we just get that x to the 4th, kind of like if you had x to the 4th and took the square root of it and also squared it. The square and the square root undo each other, and you're left with the argument inside. This is our argument inside. So we get 2 times x to the 4th plus the log of 1,000. Well, notice our trick from last time, 1, 2, 3 zeros, so that's going to be 3. And then this messy bit right here, but notice what we have. We have 8 to some power equals 1 over 64. Well, I know that 8 squared is 64. Whoa, that's how I meant to write that. And so then if you did 1 over 8 squared, you would get 1 over 64. And 1 over 8 squared is 8 to the power of negative 2. So really here what I have is 5 times negative 2, which is negative 10. And so piece this all together. I have 2x to the 4th minus 7, because the 3 and the negative 10. And in this case, we simply have an expression as our answer. Plenty to simplify in this problem here. Let's do this numerator first. So I'm going to use the plug rule again. I'm going to rewrite that coefficient 2 on my x minus 8 there. And then I have log to the power of a log base 10. So that's going to come down. So I'm going to get my 5 times x minus 8 squared. And look at that denominator. I'm going to do the same thing. I'm going to write that 2 up there. Now I have e to the power of ln. So again, inverses, they're undoing each other. And so I'm left with x squared. And so I get 5 times x squared minus 16x plus 64 all over x squared. And how does that simplify? Well, x squared over x squared is going to simplify to just 1 times 5 gives me a 5 minus 16x over x. I'm going about this in a weird way, so I'm gonna back up and I'm going to distribute that 5 in. So I'm going to get 5x squared minus 16 times 5, which I believe would make it 80x plus 64 times 5, which is 320, and this is all over x squared. So simplify it as much as you can. X squared over x squared gives me 5, minus 80x over x squared gives me 80 over x, and then plus 320 over x squared. And that is how I would write this. Another day, another problem, same idea here. Let's simplify stuff. So let's look at log base 4 of 1 over 64th. That's saying 4 to what power is 1 over 64. Well, I know that 4 cubed is 64, so 4 to the negative third would be 1 over 64. So I get 3 times negative 3 plus log base 2 of the square root of 2. Well, square root of 2 is the same as 2 to the 1 half, so that log has to be equal to 1 half. And so I get negative 9 plus 1 half, which I will write negative 17 over 2, or negative 8.5. Okay, so now we have 4 over x times e to the ln of x to the 5th. Notice how I rewrote that. Well, again, that bit is going to get rid of itself because they are inverses of each other. So we're going to get 4 over x times x to the 5th, which is going to be 4x to the 5th over x, which is 4x to the 4th. More simplifying logs. So notice now we have here 4 to what power equals 16 squared. Well, I'm going to do a little rewriting magic here. I'm going to say 4 to what power equals 4 squared, because 4 squared is 16. So now I'm saying 4 to what power equals 4 to the power of 4 by multiplying those two together. And well, then that has to be 4. So that first log is really equal to 4. And then I have minus ln of e to the 4, which is also going to simplify to 4. So I have 4 minus 4. So those two are done with each other. And so I now have just this question. 3 to what power is 1 over 9? Well, I know that 3 squared is 9, so 3 to the negative 2 is 1 over 9. So now let's look at simplifying this without a calculator. It's kind of hard because, again, think of what it's saying. This is like saying 4 to what power gives you 8. And it's hard to think about it conceptually because it's not going to be an integer. It's not going to be a whole number. So think about what we know. Think about how we know what's going on with 8. That was a really weird way to say whatever it was I was trying to say. But let's think about this. Let's go ahead and change the base of both of these numbers to base 2, because I know I can write 4 as 2 to the power of 2. That is the same as 4. So I have that to the power of x equals 8 is the same as 2 cubed. So I have 2 to the power of 2x equals 2 to the power of 3. So I have 2x equals 3, thus x equals 3 halves. So you can think about it changing the base as it is written exponentially, or you could change the base as it is written with logs. Because with logs, I can change to another base using the change of base formula, and I could write this in base 2 by saying log base 2 of 8 divided by log base 2 of 4. The base stays in the basement. And so now this is like saying, well, 2 to what power gives you 8 divided by 2 to what power gives you 4. Well, 2 to the third gives you 8, and 2 squared gives you 4. So we again get our 3 halves as an answer there. So we'll do it again here. Again, just look at what base you could use to write these numbers. It is, again, going to be base 2. So I'm going to say a log base 2 of 32 divided by log base 2 of 4. Because I know that 2 to the power of 5 gives me 32. And 2 to the power of 2 gives me 4. So I get my answer of 5 halves. Or similarly, I could rewrite this as 4 to what power gives me 32, and then rewrite it with different bases there. And again, get 2x equals 5, so x equals 5 halves. Doesn't matter if you change the base in the exponent or in the log form, because again, they are equivalent. So apparently I was all excited about base 2 on the day that I wrote these problems, because again, we could rewrite this in base 2. So I'm going to leave that 5 out front for now and change the base to log base 2. And then I need to have a 1/2 up here and a 16 down there. And 2 to what power gives me 1/2? Well, 2 to the negative first gives me 1/2. And divide that by 2 to what power gives you 16? Well, 2 to the fourth gives you 16. And then we still have that times 5, so we get negative 5 over 4. 25 to what power gives you 1/5? Well, I know that 25, the square root of 25 is 5, so I know that 25 to the 1/2 power gives me 5, so that means that 25 to the negative 1/2 power gives me 1/5. And then I have a times 8 out front, so I get 8 over 5. And I'm sorry, but I'm making mistakes again because I wrote 1/5, but my answer should have been 1/2. So that shouldn't be 8 divided by 5. That should be 8 times negative 1/2. So 8 divided by negative 2. And 8 divided by 2 is 4, so 8 divided by negative 2 is negative 4. My bad, y'all. Same idea. Let's rewrite the base here. So I'm going to say that 3 to the power of 2x is exactly this, or is equal to 1/3 is the same as 3 to the power of negative 1, 5x minus 2, and our power rule says that if we have this situation going on here, we can distribute that in to get 3 to the negative 5x plus 2, distributing in that negative 1. And so I can then say 2x equals negative 5x plus 2, so 7x equals 2, and then x equals 2 divided by 7. Okay, more. 9 and 27, notice that they can both be written base 3, so I'm going to get 3 squared is 9, and then I have my 4x minus 1 equals 3 cubed is 27, and then I have my x plus 3. So I get 8x minus 2 equals 3x plus 9, and so then 5x equals 11, and x equals 11 over 5. And now let's expand this log. So I'm going to expand this as log base 17 of 15 plus log base 17 of z, but I am going to put that 1/3 out front for that cube root there, and then plus 5 log base 17 of y minus 5 log base 17 of x. And now look, this is tricky here. It would be minus well, minus 1/2 log base 17 of y. So really that is going to be plus 1/2 log base 17 of y, using the plug rule and our multiplication and quotient rules there. And then notice I could combine that with that to get 5.5 log base 17 of y, or instead of 5.5, you could say 11 halves by combining those two.